Thank you very much for the invitation. It's a pleasure to be here, and it was a pleasure to meet Jungmook after so many years. The talk is about holonomy of pseudo-Riemannian cones and applications to killing spinors on pseudo-Riemannian manifolds. So it is based on two joint papers. So the first is joined with Dmitry Alexievsky from Edinburgh University, Anton Galay from the Eduard Czech Center in Brünn, and Thomas Leistner from the University of Hamburg. It will appear in Journal für reine und angewandte Mathematik. And the second paper is joined with Dmitry also. It will appear in a volume on special metrics and supersymmetry. So I start by recalling some basic notions which are important in this context. We consider pseudo-Riemannian manifold, so Riemannian manifold, but we do not insist on positive definiteness of the metric. And denote by H its holonomy algebra. So I recall for you that the holonomy group is the group which you obtain if you consider a parallel transport along closed curves in your manifold. So this parallel transport gives you linear transformation from the tangent space to itself, and since the connection preserves the metric, this linear transformation will be an orthogonal transformation, and you can consider the group of all such, the group generated by all such transformations, and this is called the holonomy group, and it is an important global invariant of a pseudo-Riemannian manifold. And it is known that this group is a Lie group, so it has a Lie algebra, and this is the Lie algebra of this holonomy group. We call the holonomy algebra decomposable if the tangent space contains a proper non-degenerate H-invariant subspace. So by non-degenerate I mean that the scalar product restricted to the subspace is non-degenerate. Otherwise this linear Lie algebra would be called indecomposable. So the geometric meaning of this notion is given by this Wu-de-Rham theorem. So the holonomy algebra is decomposable if and only if the manifold is decomposable as a pseudo-Riemannian product, at least locally. So in the Riemannian case, this is known as the de Rham theorem, and this has been generalized to pseudo-Riemannian manifolds by Wu. So a similar notion is that of reducible linear Lie algebra. So it's not exactly the same, but it is related. So H is called reducible if it preserves a possibly degenerate proper subspace. So in this case, we do not insist on the scalar product being non-degenerate on the subspace. So here we have more subspaces which are allowed, and otherwise we call H irreducible. So note that irreducible implies indecomposable, but not vice versa. And important notion here for pseudo-Riemannian geometry is not irreducibility, but indecomposability, because the problem is to decompose your pseudo-Riemannian manifold as a product of pseudo-Riemannian manifolds. So the important notion is here for indefinite metrics is indecomposability and not the irreducibility. Of course, for Riemannian manifolds, these two notions coincide because any subspace will be non-degenerate. Are there questions so far?
Is there an example of indecomposable, reducible manifold?
Yes, I will give a lot of such examples in the end.
And pseudo-Riemannian means any signature?
Any signature, yes.
Okay.
So can be Lorentzian, for instance, or split signature in N, so any signature. In particular, the Riemannian case is allowed. So I consider also positive definite metrics. Okay, then in the title I spoke about cones. So what is a cone? So we have the manifold M, which was pseudo-Riemannian, and we can consider the product of the base manifold M with ray R plus and call it M hat, endowed with this canonical metric. So the radial coordinate here is called R, and here we have dr square plus R square G, where G is the metric on M. This is called the metric cone over M, so you can do this for any pseudo-Riemannian manifold, and the simplest example is Euclidean space written as cone over the round sphere of constant curvature 1. And we denote the holonomy algebra of this cone by H hat. So hat always refers to the cone, and the unhatted quantities refer to the base manifold M.
Do you always get a nice point when R is 0? And what's the structure of it?
No, R0 is excluded here. So I consider only R strictly positive. And in general, at R equals 0, you have a singularity, so it's not at all allowed to put R equals 0. Of course, in this special case which I mentioned, when you have the Euclidean space as cone over the sphere, you can put in the 0 point by hand and extend this manifold in a smooth way into a complete Riemannian manifold, or pseudo-Riemannian if it is, if you do this for signature. But in general, you have the singularity of the cone. So the aim here is to relate properties of the holonomy algebra of the cone to the geometry of the base. So this is this talk is always about this. So an example of such a relation is the following. So the holonomy algebra is 0 of the cone if and only if the base manifold has constant curvature 1. So this is the case of Euclidean space written as cone over the sphere. This is a very basic relation. And so the starting point of our investigations was this theorem of Gallot from 1979, which tells us that the cone, the holonomy algebra of the cone of any complete Riemannian manifold is always irreducible or trivial. So there are only these two possibilities. Either the holonomy is irreducible, and then we have a nice list of candidates for this holonomy algebras, which was found by Berger in the 50s. So it's a famous Berger list of Riemannian irreducible holonomy groups, or otherwise H hat is 0 and no other possibility. So this is a very useful theorem because it allows to reduce some problems to this Berger list. Okay, so our question was, can we obtain such a theorem for indefinite metrics? So in the pseudo-Riemannian setting, it would be very useful to have something like this for indefinite metrics, or even for incomplete Riemannian metrics. So this was the starting problem. And so we'll see. I give you now the outline of the lecture. So the first step is to see that this theorem cannot be generalized in an immediate way to indefinite metrics. So there are some problems. You cannot just generalize it. And so I will give these counter examples which show that the positivity of the metric is used for this theorem, and also the completeness is important. So you need these both conditions to have the Gallot theorem. And then I will study what can be said. Nevertheless, we can say something about the holonomy of the cones and the decomposability or indecomposability of its holonomy. And I will give some local description of cones for which the holonomy is decomposable. So I will describe the local structure of such cones and also of the base manifold. And then if we are ready to assume to make some global assumptions like completeness or compactness, then we can obtain better results, which I will then explain. And finally, I will also speak about the case of cones with indecomposable but reducible holonomy. So here we will have several results and examples of such manifolds which are indecomposable but have reducible holonomy. And then I will apply some of the results to the study of manifolds with killing spinors. In fact, this was one of the motivations for this analysis of holonomy of the cones. In fact, the basic ideas go back to Christian Beer's classification of complete Riemannian manifolds which admit killing spinor. And so here we will obtain some classification, local classification of Riemannian manifolds admitting killing spinors, so we do not assume completeness. So using our results we can obtain a classification also for incomplete, local classification allowing incomplete Riemannian manifolds. Okay, let me start with the examples. So the first example shows that the completeness of the metric is absolutely necessary even if we are ready to restrict ourselves to positive definite metrics. So completeness is important. So we consider two Riemannian manifolds, M1, M2. To avoid some trivial cases, we assume that both are of dimension at least 2 and not both of constant curvature 1. Then we can consider this product. So M1 cross M2 cross an interval, 0 pi over 2, with this particular Riemannian metric. So it is a sort of double warped product with sine and cosine functions here. And this metric is incomplete, so you can consider the radial lines where with the parameter s going to 0, and this will approach the singularity in finite time, so this is incomplete. In fact, the cone over this manifold M is decomposable, and the holonomy is non-trivial. So this gives an example of decomposable, non-trivial holonomy of a cone. So counterexample to Gallot theorem if you drop the completeness. Okay, in fact, it turns out that the cone over this manifold M is nothing else than the product of the cones over the factors M1, M2. And the radial coordinates are related by the simple formulas. So R1 is the radial coordinate on the first cone, R2 on the second cone, and R is the radial coordinate on the cone over M. Okay, the next example shows that even if we are ready to assume completeness, geodesic completeness of our pseudo-Riemannian manifolds, we still need the positivity. So the completeness alone is not sufficient to generalize Gallot theorem, so positivity is needed for the theorem to hold. So here we consider a complete manifold, pseudo-Riemannian manifold, for instance a complete Riemannian one is okay, of dimension at least 2 and not of constant curvature 1. And then we take this formula as a metric. So again, this is some warped product now with a hyperbolic cosine function and only one factor here, n. And here we have a minus sign, minus ds square. And this metric is nice. It is a geodesically complete metric, but it is not positive definite. And again, the cone over M is decomposable, locally decomposable. In fact, this vector field, which is time-like, generates a parallel line. So this vector field shows that the holonomy is decomposable, but it is not trivial, because if it were trivial, then this cone would be flat. It's not flat.
What's R in this?
R is the additional coordinate in the construction of the cone.
Okay.
So R is always the radial line of the cone, and here we need in addition this S. So this is the base manifold M, and then in addition we have R as another parameter. Okay, so these are these examples. So we see that it is a non-trivial question to generalize this Galois theorem, so it simply doesn't work to generalize it in a direct way. And
sorry, this geodesical completeness is for any geodesic?
yes, that any geodesic should be defined for all time. Sorry? Time, like space, like whatever you like. So then we first study the local structure of Riemannian manifold with the property that the cone over it is locally decomposable. So we just start from the assumption that the cone is locally decomposable and derive some consequences and try to study what will be the structure of the base. And so we obtain this theorem. So this is without any assumption. So the only assumption is that H hat is decomposable. So no assumption on M, can be incomplete, indefinite signature, no problem. And so we can first of all prove that the holonomy of the base is always the full pseudo-orthogonal Lie algebra, SOPQ, where PQ is the signature of G. So this is very nice. So it means we always know the holonomy of the base. We don't know the holonomy of the cone. This is more or less arbitrary, only we know it's decomposable, but the holonomy of the base will be always full. And secondly, we can prove that the manifold has locally a special form, so there exists some dense open subset, M prime in M, such that any point in this open subset has a neighborhood isometric to manifold of the form AB cross N1 cross N2, where AB is a real interval with such type of metric. So the first type of metric is exactly as in the first example, so it's a double warped product with trigonometric functions. And the second example is in the second case here is a generalization of the second example, where we have here two hyperbolic functions, and here minus ds square. So this is the most general local form of such a manifold with decomposable holonomy of the cone. So this is the metric of the base. And yes, then I wanted to give a sketch of proof, so to have some idea from where we get this decomposition and what are the kind of arguments we use. So first we assume that the cone is decomposable, so we know that the holonomy algebra is decomposable, and this means that the cone is locally decomposable, and after restricting this cone, we can assume it is decomposable. So let us assume the cone is decomposable, and then we have a decomposition of the tangent bundle into two parallel orthogonal non-degenerate distributions, V1 and V2. This is exactly what it means to be decomposable. And from these decompositions, we can just decompose the vector fields we have on the manifold according to this V1 and V2. So for instance, we can decompose the radial vector field d over dr into x1 plus x2 in these distributions, and then split x1 and x2 according to the splitting of the cone in the radial lines and the base manifold. So we can decompose it as some multiple of d over dr plus the vector field tangent to the base. And similarly for x2, and then this coefficient is necessarily 1 minus alpha, and here we have minus x, because they have to add up to d over dr. So, and this is really the starting point, and very useful, even if simple decomposition. And then we see that we have special values of this function alpha, namely the values alpha equal to 0 and alpha equal to 1. And we can consider the open subset where alpha avoids these two values. So all the points in the cone M hat such that alpha is different from 0 and different from 1. And it turns out that this open subset is dense. It is a dense open subset, so this is a lemma. So in particular, it's non-empty. It's a non-empty set. And the vector fields x1, x2, and x, they are nowhere isotropic on U. So this is useful information. So whenever we consider a point in U, we know that these three vector fields are non-null. They are not isotropic. This follows from these formulas, this statement, and the fact that it is dense needs some proof. Okay, then we continue, starting from, so using this information in a moment. Of course, the method is purely differential geometric, so we should use curvature at some point. So here I wrote for you the formulas for the curvature of a metric cone. So if you put in the radial vector field d over dr into the curvature tensor of the cone r hat, you always obtain 0, so very nice. And if you take three vector fields y, z, m, or three vectors which are tangent to the base, to m, then you have such a formula. So the curvature of the cone is related to the curvature of the base and some other curvature tensor, which is in fact curvature tensor of constant curvature 1, based on the metric g hat of the cone m hat. So such a simple formula. So this is the formula for this piece. It is just the standard formula for constant curvature, for curvature tensor of constant curvature 1. And we can apply now this formula to any vector which is tangent yi, which is tangent to the distribution vi. So recall that Tm hat, the tangent bundle of the cone, is decomposed as v1 plus v2. And now we take a vector yi from vi, I equal 1 and 2. For instance, here we use y1. And to compute this, we first express x using d over dr and the vectors x1, x2, which I introduced a moment ago. D over dr was x1 plus x2, and then we had x1 is equal alpha dr plus x, and so on. So these formulas. And so here, here I express x using x2 and 1 minus alpha. So we have to write this also. So x2 equals 1 minus alpha dr minus x. And so replacing x by this expression from here, we see that first we have d over dr, but we know that the curvature tensor evaluated on d over dr gives 0. And then we have r hat of x2, y1. But x2 and y1 belong to v2 and v1, so to these two orthogonal parallel distributions, and so the curvature is 0 for such vectors. So this gives 0, and similarly we can show that r hat of x y2 is also 0 for any y2 from v2. So we see that r hat x is always 0. So this is always 0 for this special vector x, which appeared here in this decomposition. And so we obtain that rxy is equal r1 hat xy from this formula, because this term is 0. Left-hand side is 0, so this expression equal to this. And this means that we know now certain curvature operators. And now I should recall that the holonomy algebra contains in particular all curvature operators r of x, y, and also their covariant derivatives, but this is not important for the moment. And so from this we can conclude that the holonomy algebra is the full pseudo-orthogonal algebra, because these operators for curvature tensor of constant curvature here, and x, this fixed vector, generate already the full pseudo-orthogonal algebra. Here I use that g hat of x is different from 0. Otherwise this statement is not true. So I have to use here that x is not a null vector, but it is sufficient to know this in one point. And we know this at any point of u. And so it's sufficient to know that u is non-empty. But since u was a dense open set, it is non-empty, and we can find such a point. So this proves already this first part, that the holonomy of the base is full. And then to obtain this decomposition as double warped product, we need a little more. So I continue here. So I summarize now some facts which are useful and are ingredients of the proof. So this function alpha in fact turns out to be independent of the radial coordinate r. So in fact it is a pullback of a function on the base manifold M. A priori alpha was a function on the cone, but it turns out it is a function on the base M. And the open set U is in fact the product, is adapted to this decomposition of the cone as R hat cross M. U1 a subset of M. And also the vector field X is related to a vector field X tilde on the base, in fact to some gradient vector field, the gradient of alpha, up to some factor 1 over R. And on this open subset U1 of the base of M, we have some nice decomposition of the tension bundle of the base as a sum of 3 subbundles, an orthogonal sum. And these subbundles are precisely the eigenspaces of the covariant derivative of X tilde with these eigenvalues, where L is one-dimensional. It is the line generated by X, or X tilde, and EI is the intersection of TM with VI. So now this decomposition starts to appear in the formulas. At the end we want to have this double warped product, and this is the first instance where we start to see this product. And these distributions have some nice properties. So the E1, E2, and E, the sum of E1 and E2 are involutive. And the sum of EI with this line L is even parallel on this open set U1. And we can consider an integral submanifold of E, so maximal integral submanifold of E, since it is involutive, and restrict the distributions EI to this integral submanifold. And then we obtain two parallel distributions if we do this. And this will be exactly these factors M1, M2 in this double warp product decomposition. Okay, so using the flow of this gradient vector field X tilde, we can write our manifold locally as a product AB cross N, where N is a level set of the function alpha. And the metric will be of this form, so it will be orthogonal, this splitting, of the form plus or minus ds square plus metric gn on n, but this metric will depend on s at the moment. And so then we can split n as a product, n1 and 2, according to the splitting into two parallel subbundles of Tm. And the metric Gn of S decomposes as orthogonal sum of two metrics, H1 of S and H2 of S. And using the eigenspace decomposition of the covariant derivative of X tilde, which I wrote before, one can prove that the S dependence of H1 is of this form, alpha of S times G1, and here for H2, 1 minus alpha of S times G2, where G1 and G2 do not depend on S anymore. And then it remains to solve some ODE. In fact, this equation, which comes from the length of the vector X, which you can derive from these formulas of such ODE, and up to a shift in the parameter, the solutions are cosine square of S and hyperbolic cosine square of S, and this gives this final form of the metric in this double warp product.
Why S square didn't appear?
Sorry, why S?
Square.
Here you mean this square? No, this comes out of solving this equation. You obtain this cosine square.
I mean, cosine
Ah.
square and sine square are the coefficient in the polar decomposition of metric of
Yes,
of
yes.
curvature. So I suppose that a square must appear maybe somewhere.
No, not no s square. The coefficients are cosine square and sine square in this double warp product, or hyperbolic cosine square and hyperbolic sine square. And then we have the relation cosine square plus sine square equal to 1. So 1 minus alpha is the other coefficient, so 1 minus cosine square is sine square, so we get both. In fact, after shift, cosine is the same as sine. Okay, so this gives this theorem, so basically by these arguments. And now I come to the global results. So if we assume now completeness of the geodesic completeness of the manifold, we can improve this theorem. So it's not the final result. So if we assume now completeness and H hat still decomposable, then we can prove again that there exists some dense open subset such that any point in this subset has a neighborhood isometric to two cases. So we had before this two kind of double warp products, one with trigonometric functions, the other with hyperbolic functions. And in the first case, we can simply say it will be pseudo-Riemannian manifold of constant curvature. So the space will be locally pseudo-Riemannian manifold of constant curvature. So we do not need this double warp product anymore. Or in the second case, we have still such double warp product with hyperbolic functions, but we can say a little more. We can say now that G2, the second metric on this metric on N2, has constant curvature, -1 here. So this is a more precise statement, which is true if we assume here completeness. So under completeness assumption, we can improve considerably the result, which is this. And in fact, in this latter case, the cone over this manifold is a product of cones, in fact of a cone as I discussed before, and the time-like cone, where I put here before the dr square not a plus but a minus. So it's this is decomposable. Okay, and in the compact case, if we assume compact and complete, then we can have an even better conclusion. So if M is compact, complete, with decomposable holonomy group, then we can really show that the base has constant curvature and the cone is flat. So as in Gallot's theorem. So here we obtain really practically the same conclusion as in Gallot's theorem, but we have a stronger assumption. We have to assume compactness. And as a corollary, we have that if the manifold is simply connected, compact, complete, with the indefinite metric, then we can conclude the holonomy of the cone is indecomposable. And it follows from the previous theorem because indefinite pseudo-Riemannian manifold of constant curvature, simply connected, is always non-compact. So of course the sphere is compact, but this with a definite metric, if you assume that the metric is indefinite and the space is of constant curvature, simply connected, then the manifold is non-compact. So this means that here we have no other choice than to have an indecomposable cone. So this is a corollary of this theorem 3. And here, so I only give some very rough structure of the proof. So here, the proof is still purely differential geometric, but there are some global arguments here. So we consider a component of the set, open set U1, where alpha, the function alpha here, this coefficient is different from 0 and 1. And up to changing the roles of alpha and 1 minus alpha, which are symmetric here basically, we can assume that alpha is positive on this component. And then we have two cases. Either it is alpha lies between 0 and 1, or it is bigger than 1, because it avoids the values 0 and 1, so no other choice, either between 0 and 1 or bigger than 1 on this component W. And so the proof of the previous theorems for the complete case and compact case is based on the following lemma, which covers this first case. And for the second case, we have a similar lemma, but it's more complicated to state, and I do not even state it here. So it's this lemma. So we assume now that the manifold is complete, that the cone is decomposable, and that W is a component of this open set U1, such that alpha lies between 0 and 1. Then one can prove that the cone over this component is flat. And this means that the base has constant curvature 1. Okay, now I come to Vladimir's question. So what about examples with indecomposable but reducible holonomy? So cone with indecomposable, reducible holonomy. And okay, for this case, we do not have a complete description. We have a nice description for under some assumptions, but here we cannot claim to have solved the problem because, first of all, there is no classification of indecomposable holonomy groups of pseudo-Riemannian manifolds, so such classification exists only for Riemannian metrics and for Lorentzian, and nothing more. So for arbitrary signature, there is no such classification, so it's a difficult problem, and we have to make some assumptions in order to obtain some results. So now the holonomy of the cone is indecomposable but reducible. This means it preserves some non-trivial degenerate subspace. So degenerate means that the metric scalar product on this subspace is degenerate. Okay, we consider two cases. So the first case, in the first case we assume that this subspace W, which is invariant under H hat, admits an H invariant complement. In general, there's no such H invariant complement, but here in the first case we will assume this. And in the second case, we assume that the cone has Lorentzian signature. So n1, n,1 or 1, n. This is okay, but no other signature. This is the case which is nearest to the Riemannian case.
I'm sorry. Just
yes.
For me, decomposed, if it preserves, for me, decomposed manifold are those that preserve non-trivial subspace.
Non-trivial, non-degenerate subspace.
Degenerate.
Here I say
no.
degenerate.
Yeah.
So this is the point, yes. In fact, here, by this I exclude the irreducible case, because irreducible, it's easy. So you have some analog of Berger list for irreducible pseudo-Riemannian holonomy groups, but not for indecomposable. It's not solved, this problem. So there's no classification of indecomposable pseudo-Riemannian holonomy groups. Okay, therefore we restrict to these two cases, so Lorentzian, so rather near to the Riemannian case, or this case where we have a splitting into two degenerate subspaces, H invariant splitting. And in the case 1, we show that under this assumption, not only we have such a complementary subspace, but we even have locally a paracalar structure. So paracalar structure is simply a parallel skew-symmetric endomorphism field which squares to identity. So this occurred in previous talks as a product structure. So this is a product structure with a compatible metric, in fact, here. We have a Levi-Civita connection which preserves this product structure. So it is analogous to Kähler geometry, so the Kähler condition, but for such product structure. So in particular, these manifolds are symplectic, so you have the Kähler form, which is closed. Okay, so we have such J hat, and this condition implies that the metric has neutral signature, metric of the cone, so signature NN, and the dimension of the base manifold is odd. The cone is even dimensional, but the base is odd dimensional. And so we can state this a bit more clearly. So we have a one-to-one correspondence between paraclelar structures on the cone of the form G hat, the metric of the cone, and the structure J hat, it's paraclelar, paracomplex structure, and parasasakian structures on the base, G, T. T is a vector field on the base with some properties, so I will define it in a moment. And the correspondence is simply given as follows. To the vector field T on the base, we associate basically the covariant. We first of all consider this vector field as a vector field on the cone, take the covariant derivative of the cone, and obtain some endomorphism field, and this is J hat. So this is analogous to the correspondence between Sasaki manifold and a Kähler cone. So the cone over Sasaki manifold is always Kähler, and this is an analog of this correspondence. So parasasakian structure, I gave here the definition of signature n+1 is a time-like geodesic unit killing vector field such that J equal nabla T, this is now the covariant derivative on M, defines an integrable paracomplex structure on T perp. So the CR, it will be CR structure but with some additional properties. And we have a similar correspondence between para-hyperkähler cones and para-3-Sasakian manifolds. So I think you probably know hyperkähler manifolds. So these are Riemannian manifolds which admit 3 complex structures consistent with one metric. So it is Kähler in 3 different ways, and there's an analogous notion of para-hyperkähler manifolds where instead of having 3 complex structures you have 2 involutions, and the product of these 2 is a complex structure. So it is related to the group SL2 instead of SU2. And there's an analogous notion of para-3-Sasakian manifold, and we have a correspondence between para-3-Sasakian manifolds and para-hyperkähler cones. Okay, so this gives examples of such indecomposable but reducible holonomies. Parakähler and para-hyperkähler. Okay. Does it work? Okay, then okay, I should slowly come to the end. Yes. So we have some results about Lorentzian cones. So for the Lorentzian case, in fact, we can completely describe all cases, and this is due to the following effect. So any Lorentzian manifold can be, by this, just by the de Rham decomposition, we can decompose it into indecomposable manifolds. But since the signature is Lorentzian, we have a decomposition into one Lorentzian factor, and all other factors are Riemannian. And of course, for Riemannian case, we know all. So this means that the study of Lorentzian cones reduces to the study of indecomposable Lorentzian cones. So this means that this is really the general case. The case of indecomposable Lorentzian cones is practically the general case in for Lorentzian metrics. And here we have the following result. So if we assume that the cone is of signature 1n or n1 with indecomposable but reducible holonomy group, then, okay, first step is to remark that if M is simply connected, then the cone has a parallel light-like vector field, so not only a parallel light-like line, but really a parallel vector field. And we have 2 cases, either signature of the cone is 1n or n1. In the first case, the base manifold is locally of this form, so the metric is of form minus ds squared plus e to the power 2s times gn, where gn is a negative definite metric, so this means that g is also negative definite, and we consider the metric cone over negative definite manifold. This would be a Lorentzian cone. This is the first case, and in fact the completeness of the metric corresponds to the completeness of metric Gn, and to the fact that this interval AB is the full real line. And in the second case, it's a little different. If the signature is N1 and not 1N, then it looks very similar. You have again on some dense dense open subset, you can find some neighborhood of any points such that the manifold is such a product with this kind of metric. But now the metric Gn is positive definite. This means that the base is Lorentzian. So now we consider the cone over Lorentzian manifold, which is again a Lorentzian cone. So the difference between this case and this is here the base is definite, negative definite. Here the base is Lorentzian. So the first case is simpler because we have a Riemannian negative definite base, and here we have a Lorentzian base. And therefore the statement is a little different, slightly different. And we have only this implication. So if G is complete, then Gn is complete and the interval is R, but we don't know the converse. And in both cases, we can compute the holonomy of this of the cone over this local piece W. It will be such a semi-direct product of the holonomy of this auxiliary manifold N and R n minus 1, so such a affine group, affine Lie algebra. And now in the remaining, how much time do I have?
5 minutes.
5 minutes. Okay, that's perfect. So now I come to the application. So this study of holonomy of cones was motivated by the wish to understand manifolds with killing spinor, and we have several applications, but this is one of it. It gives classification of Riemannian manifolds with killing spinor. We cannot classify general pseudo-Riemannian manifolds with killing spinor. The problem is that there is no classification of indecomposable pseudo-Riemannian holonomy groups. This is the main obstruction, so there is some work to do. And in principle, we can apply our methods if we had such a classification, but for the moment it's only known for Riemannian and Lorentzian case. So let me recall the Baer classification. So Baer classified simply connected complete Riemannian spin manifolds which admit killing spinor. So if we assume that M carries a non-zero killing spinor with a killing constant different from 0, then either M is a sphere or carries one of the Baer geometries. And these are these geometries. They have some names, Sasaki-Einstein, 3 Sasaki, nearly parallel G2 or nearly Keller in 6 dimensions. And maybe to be sure that it is clear what I'm talking about, we consider the killing spinor equation. So it is this equation for a spinor. So we consider the covariant derivative of a spinor, and this should be equal to lambda, this killing number, times Clifford multiplication of the vector x with the spinor s. This is the killing spinor equation. So a special case is the equation for parallel spinors when lambda is 0. And the problem of classification of parallel spinors completely reduces to study of invariance of the holonomy group under the spinor representation. And I'm not discussing this problem now. I assume here lambda different from 0. So we consider proper killing spinors, so not parallel. And so this gives a very nice answer. So a manifold has a killing spinor basically if and only if it belongs to this list of geometries. And of course it is another problem to classify all such manifolds which have these geometries. This is a different problem. This was not solved, but what was solved is the classification of manifolds with killing spinor, so reduce it to this problem. Okay, so yes, yes, and in this Baer work already appeared this construction of the cone. So the main idea was to reformulate this equation as the equation of parallel spinors on the cone. So it turns out that this equation for killing spinors on M is equivalent to the equation of parallel spinors on the cone. So this means if you go to the cone, the equation becomes simpler and you can solve it using holonomy group methods. So this is practically the idea of proof of Baire. And then you have to identify which geometries you have on the base. Okay, so there's some case-by-case study, and these are exactly the relevant geometries. Okay, now what can we do now with our results about holonomy of general cones without assuming completeness? We can obtain a local, the general local classification of manifolds with killing spinor. So if we consider now arbitrary Riemannian spin manifold which admits a non-trivial killing spinor with killing constant lambda different from 0, then first of all we can show that the holonomy of the base is SON, so full holonomy. And second, if the cone is locally irreducible, then the base carries one of the Baire geometries locally. And if the cone is not irreducible but is locally reducible, then on a dense open subset we can write our manifold Mg in such a double warped product as before, with some factors M1, M2, which are again Riemannian manifolds which admit a non-trivial killing spinor with killing constant plus or minus lambda, or which are of dimension less or equal to 1. And this means that using this theorem we can decompose any manifold admitting a killing spinor inductively in terms of such manifolds which admit a Baire geometry or which are of dimension less or equal to 1. So by iterating this construction. So we can take a double warp product. This gives already a manifold with killing spinor, then we make another double warp product and so on. So we iterate this construction and obtain a lot of manifolds admitting killing spinors which have reducible holonomy of the cone. So they do not occur in this Baire classification, because Baire assume that the manifold is complete and then the cone is always irreducible. Yes, I think that's it. So I'm at the end.